So I want to finish up the discussion of applications of integration by talking to start with today about arc lengths and surface areas. So let's start with arc length. So we've got to make sense of length of a curve. So let's take some graph, some nice smooth curve, there we go. And as usual, I'm going to look at this curve between x equals a and x equals b. And we want to calculate the length of that curve between a and b. Right? So this is this kind of wiggly, curvy length. So let's let s be the arc length. So it's good to actually think of s as being a function of x. So it's going to be the arc length from a to x. So let's take x in there. So s of x would be this arc length going from a up to x. And of course we want to calculate s of b, the arc length all the way from a to b. But to do this, you think about it changing in little bits. So if you move up just a little increment from x to x plus delta x, we need to think about how does the arc length change when we make that little step. Okay, so we're interested in that little change in arc length. And so the thing we're trying to calculate informally, we're trying to calculate the sum as x goes from a to b, those little changes in arc length. Yeah, we don't want to sum up the delta x's. If we summed up the delta x's all the way, all we'd be doing is calculating the width of the strip. We've got to actually calculate the changes in the arc length, delta s, so they're kind of going along the diagonal there in order to get the right answer. So let's kind of zoom in on that picture. What we've really got in front of us is some sort of little right angle triangle, roughly. Right, so that's this little triangle in here. Now, of course, that's not a straight line, that's a slightly curvy line, but we're thinking about delta x being very small, and when delta x is very small, it's a good approximation to approximate that curvy line as a straight line. Okay, so this is our change in x, this is the change in y, this is the distance we're trying to calculate, delta s, the change in s, which is roughly the hypotenuse of that triangle. And so to calculate this, we're going to use Pythagoras. The hypotenuse squared, that's delta x squared plus delta y squared. And actually what I'm going to do is I'm going to write it as 1 plus delta y divided by delta x squared times, there shouldn't be a dx on the bottom, that's still a delta x because I haven't gone to the limit yet, times delta x squared. Okay, so when you just FOIL all that out, you get delta x squared, and this fraction delta y squared over delta x squared times delta x squared, that cancels and is that delta y squared. So if I square root both sides, that tells me that delta x is the square root of 1 plus delta y over delta x squared, and the square root of delta x squared is delta x. So the thing I'm trying to calculate, this kind of sum, remember this informal way I'm thinking about this, we're trying to sum up as x goes from a to b. We're trying to sum up these quantities, square root 1 plus delta y divided by delta x squared delta x. And that leads to the arc length formula. If we now take the limit, turn my kind of informal sum into an integral by letting delta x go to 0, we get that the arc length is the integral from a to b, square root 1 plus, so delta y over delta x becomes the derivative dy over dx squared dx. So that's the derivation of that arc length formula, which we're going to now use in a couple of examples. Okay, so that's the formula for calculating length of a curve. So let's do two examples of this sort of stuff. So the first example I'm going to do, I'm going to calculate, the obvious thing to do is to calculate the circumference of a circle radius A. So let me give you a circle. So let's see, axes, here's a circle, not too bad a circle. And its radius A. So remember, the equation is x squared plus y squared equals a squared. That's the graph. And what we're going to do is, well, I'm going to calculate the circumference. Actually, what I'm going to do is I'm just going to do the quarter circle. I'm going to calculate that part. And then the circumference is going to be 4 times the length of that first quadrant circumference. And to calculate that first quadrant circumference, I'm going to use the arc length formula that we just derived. So we're going from x equals 0 to x equals a. So it's 4 times the integral from 0 to a. And the formula was 1 plus dy by dx squared dx. So what we need is we need to work out dy by dx. And to do that, what I'm going to do is I'm going to take the equation of the graph, and I'm going to d by dx both sides. So when I d by dx x squared, I get 2x. When I d by dx y squared, well, here I've got to use the chain rule. D by dxing is the same as d by dying, but then you have to multiply by dy by dx. And when you d by dy, you get 2y. Then you have to multiply by dy by dx, because it's a chain rule. And when you differentiate the a squared on the right-hand side, you just get 0. So that tells me that dy by dx, rearranging this formula, so what is it? Negative 2x over negative 2y, so it's minus x over y. So 1 plus dy by dx squared is going to be 1 plus x squared over y squared. What's that? That's y squared plus x squared over y squared. But actually, y squared plus x squared, that's just a squared. So that guy is a squared over y squared. So when so this is my little calculation going on here. And so now we can go back to the main integral that we're trying to calculate. It's 4 times integral from 0 to a, the square root of 1 plus dy by dx squared, which we just calculated. So the square root of a squared over y squared, so a over y dx. Okay, so that's going to calculate for us the circumference of this circle. Okay, but hang on. I need to replace y here by x. So actually now I'm going to calculate this integral. So 0 to a, y is root a squared minus x squared. And let me see if I can calculate. So I think it's good to divide top and bottom of this fraction by a. So I'm just left with 1 on the top. And on the denominator, I'm dividing by a. So inside the square root, that means I'm dividing by a squared. So that square root becomes 1 minus x squared over a squared. Even better, why didn't I write that as x over a all squared dx? And so now here I recognize how to calculate this antiderivative because I know that the derivative of arc sine is 1 over root 1 minus the guy squared. So I'm going to kind of do a little guess and check. I'm going to try, because it's not x here, it's x over a, so I'm going to try arc sine x over a. And I'm going to kind of just, I think that's what it is, but let me differentiate to check. When you differentiate arc sine, you get 1 over root 1 minus this stuff squared, but then it's a chain rule. You've got to times by the derivative of the inside function, which is 1 over a. So I'd better put an extra a out the front because of that inside derivative. So actually I think I need 4a arc sine x over a between 0 and a. And well, arc sine of 0 is 0, so I've just got to calculate, I've got to plug in x equals a, when that's 1. Arc sine of 1 is pi by 2. And so there's my final answer. It's 2 pi a, which of course we all knew long ago is the circumference of the circle. Okay, so we're in good shape. That did that one. Perhaps you didn't know how to do this integral here. I just kind of did a guess and check. You could, another way of doing this is when you saw this and you were looking for an antiderivative, perfectly reasonable thing would have been to do a substitution, and the substitution would have been something like x equals a sine theta, and then you'd have got an a squared minus a squared sine squared theta, which would have been an a squared cos squared theta, and you'd have been in business with that substitution. You would have ended up with the same thing. But if you can kind of spot something that you recognize, it's always quicker just to kind of make this guess and check approach to calculating integration. Avoid doing the substitution if you can. So that's one example. Let's do my last example, which is kind of similar, but I'm going to calculate the surface area of a sphere of radius A. So I guess we need a picture again. So now I'm going to draw a sphere. And this is A here. So to do this, I'm going to cut it up into little discs again. So just like we did in the disk method for calculating the volume of the sphere, we're going to kind of cut up. So this is at x, and this is x plus delta x. But now I want the surface area, so I'm going to think about my little disk. Here it is, and there's the next bit of the disk. So now I'm going to make sure that I take the slant side there. I don't want to be horizontal because this is this delta s, not the delta x that we're trying to calculate. Okay, so that's our little disk. So let's zoom in on that little disk. So I'm just trying to draw this disk a little bit better. Let's see if there we go, something like that. And then it's sort of slanty. And so this is a slightly smaller circle on the right to the one on the left. So that height, the radius of this circle in my disk, that's this distance here, so that's y. And what we're going to need is we're going to need that distance, which is the change in s. Whereas, so this is exactly that same little right angle triangle that we had before. That's the change in x, but we need to go along the diagonal, the hypotenuse of that triangle, to get the change in s. So what's the surface area of this disk? That's what we need to add up. We need to work out those little curved surface areas of those thin disks. So the way to do that is to cut the disk open. Imagine making it out of a strip of paper. Cut it open and unravel it. When you do that, this disk kind of opens up into being kind of a little sort of thin. It's not necessarily, it's not a perfect rectangle, but roughly it's going to be a little rectangle where the width there, that's that delta s. And the height of this thing, I'm just going to calculate this as though it's a rectangle. The height of that, that's the circumference of that sphere when you open of that circle when you open it up, right? Which is 2 pi y. So therefore, the surface area of the disk is 2 pi y delta s. So that tells me what I've got to kind of add up. I've got to sum. Well, I guess I'm going to just do the hemisphere, so I'm going to double. I've got to sum as x goes from 0 to x equals a, 2 pi y, and you remember delta s this is the same calculation as we just had. That's 1 plus delta y by delta x squared delta y. So it's almost the same as the arc length formula. What we deduce is the area is twice the integral from 0 to a, 2 pi y square root 1 plus dy by dx squared. Why did I put delta y at the end? That was meant to be a delta x at the end. There we go. That was just exactly the same formula in here. That was our formula for delta s, which we worked out back when we were working out the general arc length formula. It's just the same game going on here. 1 plus delta y by delta x squared, delta x. So when you pass to the limit, it becomes 1 plus dy by dx squared, all square rooted dx. So that's what we've got to calculate. This piece right here, it's just exactly the same as we had when we were doing the circumference of the circle. It's exactly this 1 plus dy by dx squared was a squared over y squared. If you got to square root, it was just exactly the same a over y as we had before. So the integral that we've got to calculate, let me see, it's 4 pi. Moving my scalars out the front, I've got a y, and then that was a over y dx. And this is very nice because the y's cancel, and actually it's just a constant. I just get 4 pi a. So I've got to find an antiderivative of the a, that constant inside. An antiderivative of the constant is just constant times x, which we've got to evaluate between 0 and a. When you plug in 0, you get 0, so it's just plugging in a, and you get 4 pi a squared, which you probably recognize as the formula for the circumference of a sphere of radius a. So somehow that one, the last one I'm doing, is the easiest one of all. There's really nothing to the integration because it just all cancels and it's just integrating a constant. Okay, I think that's plenty of practice of integration for now. Let's move forward onto the next topic. So I've finished my review of differentiation and integration. We've talked a little bit about the fundamental theorem of calculus, and we've done a bunch of examples of calculating areas and volumes and curve lengths, deriving all the classical formulas which were actually known way before fundamental theorem of calculus due to Archimedes and other ancients. Oh, and I also talked a little bit about Fermat's theorem, a kind of forerunner of the inverse power rule, which I felt would have suggested the connection between integration and differentiation, would have suggested the fundamental theorem of calculus in the first place. So what next? Well, the next topic is another piece of classical mathematics. I want to talk for the rest of today about conic sections. This was also a piece of classical mathematics. The name that springs to mind is Apollonius. This is kind of geometry which would have been well known for thousands of years, actually. But by the time Newton was starting to think about setting up calculus, this mathematics of conic sections is the sort of thing he would have been taught when he was training. So I always think when you're kind of thinking about the history of these things, it's good to have a vague idea of the sort of tools that would have been available to Newton and Leibniz at the birth of calculus. And certainly this classical theory of conic sections is something they would have known really rather well. So what's a conic section? Well, there's 3 conic sections basically. They're called the ellipse, the parabola, and the hyperbola. And I'm not very good at Greek, but I think ellipse translates roughly to defect. Parabola in ancient Greek translates roughly to alongside. And hyperbola, well, you know that word, but still in use in English today. I think it translates as excess. So the 3 conic sections, what have they got to do with cones? Well, let me draw you a cone. Here we go. reasonable looking cone. And so this is a mathematical cone, so it kind of goes up to infinity and it goes down to infinity. I've just drawn a little piece of it. And there's 3 different conic sections that we're talking about. There's 3 interesting ones anyway. So let's try and draw them in 3 different pictures. So the first one is the ellipse. So what you do is you take this cone and then you slice through it with a plane, kind of some sort of diagonal angle here. And that plane will slice through the cone, and so you imagine kind of make the cone out of wood or something like that and saw through it in this plane at this angle, and then open it up and look at the cross section that you're left with. That's the conic section. And I think you can sort of roughly see just from intuition that when you kind of open that up, you would be getting some sort of curve like that, which certainly looks a little bit like an ellipse, right? That's all we see at this point. That's the first type of conic section. The next type of conic section, which is going to be the parabola, is when the plane slicing through the cone is exactly parallel. That didn't work very well, there we go. Exactly parallel. One last try. I'm quite good at these pictures usually. Exactly parallel to the slant of the slant edge of the cone there. And so here will be the conic section in this case, and you can see it's sort of going to come out and it's sort of going to go up to infinity, and there we are behind. There we go. And that looks a bit parabola-like. And then the final type of conic section is when your plane slicing through goes both through the top and the bottom of the cone. Boy, this is not going so well today. There we go. Okay, so there's that slicing cone. So this time the conic section is going to look a little bit like, so here we are, we've got, so in the top half it's sort of some curve that sort of goes like that, and in the bottom half it's sort of some curve that kind of goes like that. That's not a great picture, but probably you know already what ellipses, parabolas and hyperbolas are meant to look like, and that's roughly what we're seeing here. So let me try and draw those on axes that you're used to. So the ellipse looks something like that. The parabola, let me see, I'm going to draw my parabola this way. It doesn't really matter what you're used to. And hyperbolas actually have 2 asymptotes, which are these dotted lines that I've drawn in, and they kind of go like this and approach that asymptote and the mirror image. Let me try and draw that. The mirror image, there we go, approaching that asymptote. Okay, so this is roughly what we're seeing in these conic sections. And what I'd like to do is actually prove, I'd like to derive the equations of these graphs. So you probably already have a good idea of what the equations of ellipses, parabolas and hyperbolas look like. I think the standard rectangular form for the ellipse, like I've drawn it, has equation x squared over a squared plus y squared over b squared equals 1. So this would be a and this would be b. And I guess a should be bigger than b. So this is called the major axis and the minor axis of the ellipse. Of course, if a equals b, that's just the unit circle. So a circle is a special case of an ellipse. The parabola, I've drawn this, maybe it looks a little bit weird to you. I've drawn it going to the right. Maybe you're more used to drawing like y equals x squared going upwards. But let's see, this would be something like y squared equals 4ax. That's my preferred general form for a parabola. And the equation of the hyperbola is like the ellipse, except instead of being a plus there, there's a minus. X squared over a squared minus y squared over b squared equals 1. So for ellipse, x squared and y squared both come with positive coefficients, And for hyperbola, x squared and y squared, one's positive, one's negative. So there we go. So again, that would be a, and that would be minus a. Well, so what I'd like to convince you of is that indeed the conic section, which from the picture all you see is that it looks a bit like an ellipse. I want to prove to you that it's exactly an ellipse. It exactly has an equation of this form. And similarly for the parabola and the hyperbola. So we've actually got to do a calculation to find these equations. So we want to calculate the equations of these graphs, starting from the conic section picture that I drew at the top. So I'm going to try and convince you that indeed those are the right equations. So let's take our cone one more time. So let me see that. So I'm just kind of drawing a flat cross section of that picture now. So there was the cone. Let's maybe make it look a little bit like a cone. That would be good, wouldn't it? Right, so there was my cone that I had before. And I'm going to call that the x-axis. I'm actually going to call that the z-axis. And so the y-axis in my picture is going into the page, because we're in 3 dimensions with this problem. And then I guess I'm gonna so that's that slant edge of the cone. I'm going to assume that this is of slope. I'm going to call that slope maybe L. So that's the slope of the side of the cone. And then we're taking a plane and we're cutting through this picture with some plane. There we go. I'm just kind of drawing the plane. So the plane is just coming straight out of the page, or straight out and in. So I'm just sort of drawing a little bit of a cross section. I don't know if you can picture this. So the plane really is sort of, it's kind of coming in out of the page like this in that y direction. You can sort of see the plane slicing through there. And let me see. Let's make the slope of that. Let's call that slope m. So I've just drawn the case when the slope of the plane slicing through is my m is smaller than L. That's going to be the ellipse case, but there's also going to be when those two slopes are the same, the parabola case, and when the slope m is bigger than L. That'll be the hyperbola case, right? So these are kind of the 3 cases. I'm going to focus on the ellipse case mainly, but so there's the picture. Okay, so we need to know the equation of the cone. Well, the cone is the line z equals Lx. Remember, L is the slope. So that right there, and it's a bit weird I'm doing this in the xz plane. That's z equals Lx. It's that line rotated around the z-axis. So if you think about that, you see that the equation of this surface is going to be z is going to be, well, I guess it's going to be plus or minus square root x squared plus y squared. When you rotate that around the z-axis, that's what you get. Or better would be to say z squared is, well, I missed the L there. Let's sneak that back in. Sorry, that was the Lx. So it's plus or minus L root x squared minus y squared when you rotate, right? So when y is 0, that square root x squared is just giving us x again. We're recovering z equals plus L or z equals minus L, which are those 2 straight lines, those 2 slant sides in the xz plane, but we've kind of rotated this around the z-axis. better way to write this is z squared is L squared x squared plus y squared. Okay, so that's the equation of the cone, that curved surface. And the plane, that has equation, well, if you just saw this straight line in the xz plane, you would say that is z equals mx plus d, where that d would be that intercept, right? That z-axis intercept. But this is an equation in 3 variables, x, y, and z. It's valid for all values of y, right? So it's just this straight line, z equals mx plus d, and it's just coming out of the page in the y direction because it's all values of y satisfy that equation. Okay, so that's the plane. And what we need to do, we need to compute the intersection of this cone and this plane. And that's easy enough to do. All we have to do is take z in the plane and plug it in as the z in the equation of the cone. So the intersection happens when, instead of writing z squared, I'm going to replace z by mx plus d, when that is equal to L squared x squared plus y squared. Okay, so that's the equation that we're after. Let me maybe just rewrite it a little tiny bit. If I FOIL everything out and move things over to the other side, so on the right hand side I've got L squared x squared plus L squared y squared. I switched the two sides around, I don't know why I did that. The left hand side, when I FOIL it out, is m squared x squared plus 2mxd plus d squared. So if I bring all the x's over to the left, what have I got? I've got L squared minus m squared x squared plus 2mxd plus L squared y squared is d squared. So I think that's almost what I want. The important thing to note about this equation, really all that's important, is to realize that this is just a sort of a general quadratic equation. It's got x squareds, it's got x's, it's got y squareds, and that's really what conic sections are, these ellipses, hyperbolas, and parabolas. They're kind of these sort of general quadratic equations, the curves that they define. But let me see. This is not at all bad. This is going to turn into the equation that we want. I guess strictly speaking, I mean, what am I doing here? It's just a little bit confusing. I mean, I'm kind of this red plane that I've drawn. Let me maybe draw this plane a little bit better. And so I've drawn that kind of red plane at that slope. You sort of see it there, and we're looking at this this conic section in there. So this is this shape. We're trying to see that it's the ellipse. There it is. There's our conic section in there. I mean, if you're really kind of thinking carefully, so this is the y direction. That's the axis inside that plane, and really we want the x-axis inside that plane, right? We want that to be our x direction, and we want to work out the equation of that. But the way I've done it, I've kind of my x is actually not inside that red plane. My x is in this direction, so my x is actually kind of coming out of that plane a little bit down below. So we've actually kind of got that. That's what x is in this equation. So I guess what I've done is I've projected this slanty plane onto the xy plane, this horizontal plane in my picture. But somehow that's not really a big deal. I mean, that angle theta, what is it? Tan theta equals m. That's that slope of that red plane. And all you have to do is replace the x. So I'm just going to make a little note here, what we should really do. We should really scale these x's. think you need to scale it by like x cos, you need to replace all your x's by x cos theta to get the actual xy equations inside this red plane. But scaling, that's just stretching in the x direction. It's not going to change the nature of the equations that we're doing. Okay, so I'm not really too bothered about that. I'm just going to work with this equation right here. Okay, so but one thing you can see right away is, for example, if the slope m was 0, so that our slicing plane was exactly horizontal, then there wouldn't be any scaling necessary here because cos theta would be 1. And in that case, when m is 0, what have we got? We've got L squared x squared and we've got L squared y squared. And you probably already see that that's the equation of a circle in that case. But let's see what's going on in general. So let's just copy that over onto the next page. So how would I rearrange this a little bit? Let me see. I think what I would normally do is I don't really like this extra x term, so I would kind of complete the square. So I would try and write that as some x all squared, so that when I square it, it exactly swallows up that x term. So I think I'd have to add md over L squared minus m squared. I don't want to do the algebra for very long. On the right hand side I had d squared. When you square this out, it gives you the correct x squared, and twice the product gives us that term, but you get this term squared, which we don't want, so I better add that again, so there's an extra m squared d squared over L squared minus m squared. I'm going to go very quickly through the algebra because it's not that fun. So what have I got? I've got actually overall L squared d squared over L squared minus m squared. And then what I want to do is simply replace this quantity in here. I'm going to change the x. I'm going to replace that by just x. So basically what I'm doing is I'm shifting the origin. We then get L squared minus m squared x squared plus L squared y squared is this nasty quantity, L squared d squared over L squared minus m squared. Okay, so that's completing the square tells me how to shift the origin to cancel out the x part of this equation. So now we've just got x squareds, y squareds, and constants. And now you can see in the three cases, in case 1, so case 1 was the ellipse case. That was when m is less than L. So in that case, what's going on? If m is less than L, that's a positive number, that's a positive number, and that's a positive number. So this equation has the form. So if I divide everything through by this quantity, I'll get a positive multiple of x squared, a positive multiple of y squared equals 1. So basically I get the form x squared over a squared plus y squared over b squared equals 1. So indeed, it's the ellipse. In the case m equals L, well, then this is just a 0. Actually, in that case, this completing the square trick I did, I shouldn't have done it. I should have just stuck with the original equation, right? Because, I needed to have x squareds around to complete the square. If m equals L, that's just simply 0. And this is all the equation that we've got. And you see I can shift my origin again and I get y squared is a multiple of x. So in that case, you see that the equation looks roughly like y squared equals 4ax after shifting origin. The completing the square trick doesn't work in this case. And then the final case is when m is bigger than L. In that case, completing the square was totally fine, but now L squared minus m squared is negative. So this is a negative x squared plus y squared, and this right-hand side is negative. So when you divide through by that right-hand side, that's a negative number. To get 1 on the right, this gives you some positive multiple of x squared minus a positive multiple of y squared. And so the equation turns into this sort of form: x squared over a squared minus y squared over b squared equals 1. Indeed, it's the equation we were expecting of the hyperbola in that form. Okay, so I mean, I didn't really need to do all of that complicated algebra and analysis. Really, as soon as we saw that the equation was a quadratic, when we intersected this surface and this plane, that's already enough to see that you've got a conic section. But I wanted to just go a little bit further to see that it was an ellipse, parabola, or hyperbola in the three cases. So that proves that the conic sections are indeed those graphs with those equations in Cartesian coordinates. But, well, you know, that wasn't terribly pleasant. There was some nasty algebra going on. Really, that was the wrong approach. So let me finish by trying to show you really what's the right approach. The right approach really is to do more classical Euclidean geometry. And this is certainly the way it would have been done in Newton's time. This is how it would have been worked out by the ancient Greeks, by Apollonius. They didn't even have x's and y's and Cartesian coordinates and all of that stuff. But I did it that way first because I think it's what we're more familiar with now. So I'm just going to explain this just in the case of the ellipse. I'll talk more about parabolas, and I guess I might talk a bit more about hyperbolas, but in the future, not today. So in the ellipse case, what we need to know is we need to know really what's the right way of that the ellipse had this equation in standard rectangular coordinates. So usually A is bigger than B. So I already drew this picture. So here was our ellipse. Good enough for now. And this would be A, that would be minus A, B, minus B. So actually the point about the ellipse is that there's two special points called the foci, F1 and F2. And the points on the ellipse have the property that the distance from P to the first focus plus the distance from P to the second focus is a constant. Let's just think what that constant is. Let's just think about this particular point on the ellipse. How far is it from the first focus, that distance? How far is it from the second focus? What's the sum of those two distances? Well, it's the same as that distance plus that distance. So for this special point on the ellipse, the sum of the distances to the two foci for this is the same as this distance, which is 2a. So that's kind of the correct Euclidean geometry way of defining the ellipse. It's the locus of points whose distances to two different foci sum to a constant. And I'll get you to investigate that a little bit on the homework this week and prove that indeed that does have this Cartesian equation, and I think I'll get you to work out actually the coordinates of the foci in terms of A and B at the same time. And I'll talk more about this later on. But you've probably seen that description of an ellipse. The way you draw an ellipse in practice is you take a piece of string and you pin one end at F1 and the other end at F2, and then you pull your string taut with your pencil P, and then you just kind of move your pencil around so that the string stays taut, and then that'll transcribe the ellipse perfectly. If the two foci are at the origin, then of course you're just drawing a circle by that method, but this is the right way to draw ellipse. So what I want to do, just to finish with, I want to prove the conic section is an ellipse according to this geometric description. This one right here. So let me have a shot at doing that. So we really just need one good picture, and then it's really quite nice and clean to see this in one go. So I'm going to try and draw a nice big cone, and then I need my plane slicing through it. I'm doing just the ellipse case. You can let's color it in. I think it'll look better if we color it in. You can do the hyperbola and parabola very similarly. There we go, that's my plane. And what I want to do is, so this is the bit that's hard to draw. So I want you to imagine underneath here putting a little spherical balloon and inflating that balloon. So that's inside the cone and underneath the plane. And you inflate it with just enough air so that that balloon gets trapped. It exactly touches the plane at the top and it touches the sides of the cone. So there it's going to kind of touch at somewhere like that point. There we go, right? So that's the little balloon. I sort of stuck it inside, and you exactly move it and that will touch the plane at some point, which I'm going to call point F1. And then you take another spherical balloon and you put it inside and you inflate it so that it exactly touches the plane. Okay, this is too big to fit into my picture. You want it to exactly touch the sides of the cone, exactly touch the plane. There we go. It's not quite going to fit, so it's not going to look like a sphere, but it's meant to be a sphere. Yeah, I'm struggling with my picture here, so let's do one last effort, but it's not going to fit in the picture, right? So that's meant to be a perfect sphere, and that'll exactly touch at a second point, F2. Great. So that calculates two different points inside that plane. And now let's think finally about a point. So here's our conic section. So it's somewhere like that, right? That's our conic section. That didn't work very well. I better kind of abandon my picture because I'm not doing a great picture. There we go. Something like that. And let's think about a point P. So P is a point on the conic section, and F1 and F2, those are the foci calculated by inserting spheres above and below. Okay, and then I need just a couple more points in this picture. I need this point here, I'm going to call that x2, and this point here I'm going to call it x1. So those are the points where those spheres touch the cone. And so the observation that I want to make is that the distance px1 equals pf1. So it may be easiest to see it at the bottom here. So px1 is this distance right here. Pf1 is that distance right there. You see there's that center of that circle. So these are radii, so they're at right angles, and I think you know right away from your Euclidean geometry that those two lengths are the same. Similarly, px2 is pf2. Okay, so it might not look it in my picture, but that's because the distances are foreshortened in my not very good drawing. Therefore, if I want to calculate the distance from P to F1 plus the distance from P to F2, it's equal to the distance from P to X1 plus the distance from P to X2, but that's just P to X1, P to X2, that's just the distance between X1 and X2. And that is a constant. That's the thing I was calling 2a before. Why is that a constant? Well, that's just, this is just the circle around the cone at x2. This is the circle around the cone at x1. That constant, x1, x2, that's just how far those two circles apart measured along the surface of the cone. And so in that way, I've proved that the points P on the conic section, they all have this property: the distance from P to the first focus in the plane plus the distance from P to the second focus is a constant. And that is the geometric definition of ellipse. Hopefully you can see my picture. It's not terribly good.